So here in this video, I want to talk a little bit about atomic orbitals, and the file I'm using, this PDF file called Atomic Orbitals, is available on Blackboard, so you can download the file as well. So I'm going to go to full screen here, and the first thing we need to realize about atomic orbitals is that because the atom is roughly spherical, it's most convenient to work in spherical polar coordinates rather than in Cartesian coordinates. So if you're not familiar with spherical polar coordinates, there are three variables necessary to define a point in three-dimensional space, but instead of an x, y, and z component, we have r, which is the distance of the point from the origin, which is the center of the nucleus, theta, which is the angle between the positive z-axis and the line segment connecting the origin to the point, and then phi, which is the angle between the positive y-axis and the perpendicular. If you drop a perpendicular from that point into the xy plane, that line has an angle with the x-axis, and that's phi. So the conversion to go from the spherical polar coordinates back to Cartesian coordinates is that z, the z component here of the line segment, is r times cosine theta. Since the cosine of theta is the adjacent, which is this z component, over the hypotenuse r, then z is equal to r cosine theta, because cosine theta is equal to the z component over the hypotenuse r. And x is equal to r sine theta, right? The r sine theta component is what puts it into the xy plane, because the x component, right, the xy component of this line segment here, which you see being dropped into the perpendicular, sine is defined as opposite over hypotenuse, right? And so the opposite is the x component, right? It's this piece here, or opposite the theta, and the r is the hypotenuse again. So r sine theta is this distance from the origin here to the point where you drop the perpendicular. And then there's a cosine theta, or cosine phi rather, for the x component, right? Because this x component of that line segment is opposite over hypotenuse again, so that it's cosine phi is equal to x over r sine theta, right? X being the x component, the adjacent, r sine theta being this hypotenuse. And the y component is r sine theta sine phi, because the y component of this, right, which is this piece here that connects the angle, that's the opposite of the hypotenuse. The opposite is y, the hypotenuse is r sine theta again. So x is r sine theta cosine phi, y is r sine theta sine phi, and z is r cosine theta. We can write the Hamiltonian operator then for the hydrogen atom, and this is the Schrödinger equation. The Schrödinger equation tells us that the Hamiltonian operator acts on a wave function, the wave function being the description in waveform of the electron. The Hamiltonian operator acts on that wave function to return a scalar times the wave function, and that scalar is the energy. So h hat, which is the Hamiltonian operator, times psi, the wave function, is equal to E times psi. Those energies can be measured spectroscopically, so we know what the energy levels are in the hydrogen atom, for example. So it's a matter of defining a wave function that meets that equation. And here's the Hamiltonian operator. It's a complex differential equation, partial differential equation in r and theta and phi. This is the kinetic portion, and then there's a potential energy portion here, which is simply equal to q squared, where q is the charge on the nucleus, times 4 pi epsilon 0 times r. So the Hamiltonian operator is quite complicated. The differential equation is very complicated. We don't need to know, fortunately, how to solve that differential equation. What we do need to know is what the results look like. And here is what the results look like. The hydrogen-like wave functions for a one-electron system. The Schrödinger equation can only be solved accurately for a one-electron system. So Z, right, that's the charge on the nucleus, so +1 for hydrogen, +2 for helium, plus, as the monocation, +3 for lithium as the dication, A is the Bohr radius. That is the most probable distance for finding the 1s electron in the hydrogen atom. And then, of course, R is the distance from the electron to the nucleus. So you'll notice that for the 1s orbital, the 2s orbital, and the 3s orbital, there's a kind of a numerical piece, 1 over pi to the 1/2, and then you go to 4 times 2 pi to the 1/2, and then 81 times 3 pi to the 1/2, but it's a numerical part. There's always a dependence on z over a to the 3/2 for any of the s orbitals. And then there's a exponential, e to the minus zr over a for the 1s orbital, minus zr over 2a for the 2s orbital, minus zr over 3a for the 3s orbital. So this 1 versus 2 versus 3 in the denominator explains why, as the principal quantum number, which is the first number here, n equals 1, n equals 2, n equals 3, as that principal quantum number increases, the exponential decay decays more slowly, which means the orbital extends further from the nucleus, right? And we know that n, the principal quantum number, defines the size of the orbital, and a larger value for n means that the orbital extends further from the nucleus. So the 1s orbital is smaller than the 2s orbital, the 2s orbital is smaller than the 3s orbital, and that's because of this principal quantum number that appears in the denominator of this exponential part. You'll also notice that there's a polynomial in front, in between this numerical value and the exponential part, right? There's actually no polynomial in front of the 1s. In front of the 2s, there's a linear equation, 2 minus zr over a. So there is a value for r where zr over a is equal to 2, which means that this linear piece here is 0. That means there is a value for r at which the magnitude of this wave function is 0. And we refer to that as a node. There is 0 probability of finding the electron at that distance r from the nucleus, where this 2 minus z over a becomes 0. As you go to the 3s orbital, that polynomial becomes a quadratic. And so now there are going to be 2 roots for that quadratic, 2 values of r, where this quadratic has a value of 0, which means that the wave function has a value of 0, which means there are going to be 2 nodes, radial nodes, at 2 different distances for r. So the number of radial nodes keeps going up as the principal quantum number does. And there's no angular dependence on any of these s orbitals. And that means that all of the nodes are radial nodes. The number of nodes is always equal to the principal quantum number minus 1. So for a principal quantum number of 1, there will be 0 nodes. For a principal quantum number of 2, there will be 1 node. And for a principal quantum number of 3, there will be 2 nodes. And for an azimuthal quantum number of 0, right, S has the azimuthal quantum number L equals 0. P has L equals 1, and D has L equal 2, right? Because the azimuthal quantum number can vary from 0 up until n minus 1. So there is only an s orbital for the n equals 1 shell. There is an s orbital and a p orbital for the n equals 2 shell, because the value of the azimuthal quantum number L can be 0, 2s, or 1, the 2p. And then the magnetic quantum number m sub L can vary from minus L to plus L through 0. So for L equals 1, it can be minus 1, 0, or plus 1, 3 different p orbitals. And for L equals 2, the d orbitals, it has 5 values, minus 1, minus 2, minus 2, minus 1, 0, plus 1, plus 2. Right? So the number of orbitals in the subshell goes up as the azimuthal quantum number goes up, and the size of the orbital goes up as the principal quantum number goes up. The principal quantum number tells us about the size. The azimuthal quantum number tells us about the shape, right? Tells us that, for example, the p orbitals all have that dumbbell shape where there's a positive lobe and a negative lobe. And then the magnetic quantum number tells us which direction it lies in. So, for example, the 2pz orbital will lie on the z-axis, and the 2px orbital will lie on the x-axis, and the 2py orbital will lie on the y-axis. If you recall that r cosine theta is the z component in the spherical polar coordinate system, you'll notice that there's an r cosine theta factor here in the pz orbital. So there is a value for theta where cosine theta is equal to 0, right? If theta is equal to 90 degrees, which would make the angle between the positive z-axis and the line segment 90 degrees, that means it lies in the xy plane, right? In the xy plane, z is equal to 0, r cosine theta is equal to 0, 90 degrees, which means there's an angular node here that lies in the xy plane. Z equals 0, the xy plane is a node, right? For r cosine phi, right, x is equal to 0 for cosine phi, right? If phi is equal to 90 degrees, that puts you along the y-axis, right? X is equal to 0. So when x is equal to 0, the px orbital has a node at x equals 0, and that is the yz plane. And when theta is 180 or 0, which puts it on the x-axis, right, then r sine theta, or sorry, sine phi is equal to 0, which means y is equal to 0, and at y equals 0, the xz plane is a node. So the node for the pz orbital is the xy plane, for the px orbital is the yz plane, and for the py orbital is the xz plane. The subscript, z, x, or y, tells you which plane is the node. Z equals 0 for pz, x equals 0 for px, and y equals 0 for py. Right? And we can see that based on the angular dependence. You'll notice that the 3p orbitals, right, 3pz has the r cosine theta, the same r cosine theta that you saw in 2pz. The sine theta cosine phi part, right, the same as you saw in the px, and the sine theta sine phi for 3py, same as you saw in the 2py. So it's the same angular dependence. Any pz orbital will have a node at z equals 0, which is the xy plane. Any px orbital will have a node at x equals 0, which is the yz plane, and any py orbital will have a node in the xz plane, right, which is y equals 0. What you'll notice, though, is that there are no radial nodes, right? There's no kind of polynomial function. There's a numerical piece, and then there's this exponential piece, but there's no polynomial function in the 2p, because the total number of nodes is always equal to n minus 1, which for n equals 2 is one node, and there's an angular node here, right? The number of angular nodes is always equal to the azimuthal quantum number. So for L equals 1, a p orbital, there's one angular node. For n equals 3, there are 2 total nodes, but since L is equal to 1, only one of those is an angular node. There's a polynomial here, a linear equation. There is a value for r where zr over a is equal to 6, which means this 6 minus zr over a is equal to 0. So there is a value for r. There is a radial node as well. Right? For the 3d orbitals, you'll notice that there's no polynomial, right? There's a numerical piece, there's an exponential piece, but then there are now multiple angular dependencies. There's sine theta, cosine theta. There are going to be 2 angular nodes, because there's a value for theta where sine theta is equal to 0, and there's a value for theta where cosine theta is equal to 0. So you're actually going to have, for 3D xz, 2 different nodes. That's going to lie in the xz plane, right? But it's going to have nodes at xy plane and yz plane. The 3D yz is going to have nodes in the xy plane and the xz plane. And the 3D xy is going to have nodes in the xz plane and the yz plane. 3D x squared minus y squared will have 2 nodes, x equals y and x equals minus y. So the lobes of this orbital actually lie on the x-axis and the y-axis. And then the 3D z squared is the weird one. It's got the cosine squared theta minus 1 in there. That's the one that has the torus, and we'll see that shortly. Right? So you don't need to memorize these equations, of course, but you need to understand that the shape of the orbital is controlled by the azimuthal quantum number, right? The size of the orbital by the principal quantum number, and as the principal quantum number goes up, notice that the exponential decay decays more slowly, right? All of the n equals 3 orbitals have that 3a in the denominator, which means they all extend further from the nucleus. and then there's this polynomial piece, right? A 4pz orbital would have a quadratic in front of it rather than this linear equation. So here are the n equals 1, n equals 2, and n equals 3 probability functions. The probability function is psi squared. Probability is a point for the azimuthal quantum number of 0. So these are all s orbitals. And you notice that the probability function, right, has 0 nodes for the 1s orbital. It has this one radial node here for the 2s orbital, and these 2 radial nodes, right, places that looks like an onion skin where the radius can't be. The radial probability distribution is the sum of all the individual little probability functions at any volume element, right? And so the radial probability function takes into account not only the probability of finding the electron in an individual volume element at a certain distance, but also how many volume elements there are at that distance. The further you get from the nucleus, the larger number of individual volume elements of the same size there are at that distance. And you can think of that if you peel off an onion, the outer layer of the onion flesh is going to be a much larger total volume than the inner layer of the onion flesh, right? So even though the probability of finding the electron in a volume element close to the nucleus is much larger, the total probability of finding an electron in any of those volume elements at that distance, it's obviously 0, because at the single point in the center of the nucleus there is no volume, right? And I use the hamburger chain analogy here. There are far more McDonald's than there are Five Guys, and far more Five Guys than there are Hamburger Inn. There's only one Hamburger Inn. It's probably got the best burgers, so the probability of finding someone in the Hamburger Inn versus a McDonald's versus the Five Guys is larger, right? The total number of people in the Hamburger Inn is probably larger than the total number of people in any individual Five Guy or McDonald's restaurants. But the total number of people in the Five Guys restaurants, because there are so many more of them, is much larger than the total number of people in the Hamburger Inn, and the total number of people in the McDonald's restaurants is larger still because of the vast number of McDonald's restaurants, even though the hamburgers are allowed. So the radial probability function is what we're really interested in. That's what we're going to indicate with these kind of blobs, right? And there's a most probable distance that gradually increases as you increase the principal quantum number. But you'll notice that there's a very important inner lobe here. Even though the most probable distance is larger for n equals 2 than it is for n equals 1, sometimes that electron is very close to the nucleus where it feels a full nuclear charge. And you recall from Gen Chem, that's known as penetration. And that's why the s orbital is lower in energy than the p orbital. Here's the corresponding p orbital. This is the radial distribution, radial probability distribution, right? As you go out along the axis that the orbital lies on, you'll notice that the most probable distance for the 2p orbital is actually a smaller value than the most probable distance for the 2s orbital. But this inner lobe is inside any of these n equals 2. When the electron is in this inner lobe, it's held more tightly by the nucleus, and so the 2s orbital has a lower energy because the electron feels the full nuclear charge. The effective nuclear charge is slightly larger for the 2s orbital than it is for the 2p orbital because of this penetrating lobe, right? And for the 3p orbital, it's even more important because the charge on the nucleus is going up as you increase the principal quantum number. So here is the pz orbital, right, shown as the probability function, and then this shows the px, the py, and the pz orbitals kind of all overlapping with each other. It's arbitrary what the shape of the orbital look like because we know that this exponential decay never reaches the axis. So if you want to have 100% probability of finding the electron, you have to include all space, but we generally arbitrarily cut it at something like 90% of the area, or 95%, or maybe 98% of the area. The shape of the orbital doesn't change the overall form of the orbital doesn't change, but the boundaries change as you decide whether you want 90 or 95 or 98% probability. You'll gradually increase the size of the lobe as you go to a larger probability. So those are the s and p orbitals. When we go to the d orbitals, you'll notice that for n equals 3, L equals 2, right? This most probable distance is much larger than the most probable distance for the n equals 3 orbital here, right? The most probable distance is about 7 here, and the most probable distance is more like 5 here, right? So as you gradually increase the azimuthal quantum number, the most probable distance is kind of inside the s orbital. But remember, the s orbital has those penetrating lobes, which is why it's lower in energy, and the p orbital's penetrating lobe for the n equals 3, L equals 1 situation would also be in here. So this shows the dyz orbital with its nodes at the xy plane and the xz plane, the two planes that are not represented by the plane here, the yz plane, right? And then kind of changing to a smaller value for the total probability. We change the kind of size of the lobe a little bit. So dyz has those nodes, right, on those two planes that are shown here. dxz then has the xy plane and the yz plane as their nodes, and dxy has the xz and the yz plane, right? Everything that doesn't include the xy plane. So this one lies in the xy plane, this one lies in the xz plane, this one lies in the yz plane. Dx squared minus y squared also lies in the xy plane, but on axis instead of off axis. So now where x squared minus y squared is equal to 0, right? So for x equals y and x equals minus y, x squared minus y squared will equal 0, right? And the two nodes are where x squared minus y squared equals 0 at x equals y and x equals minus y. And then the dz squared is really kind of weird. It's got this torus here that lies in the xy plane, and then the orbital lobes. And this shows all of the d orbitals overlaid on each other, showing that it's overall kind of symmetrical when all of them are filled. Here I've shown some plots that show you what the p orbitals look like where there's both a angular node and a radial node. So this is the 3pz orbital, which means that it has a node at z equals 0, which is the xy plane. That's the angular node, but then it also has a radial node, right? So you've got kind of an inner lobe and an outer lobe, and the sign changes as you go across that node, and then the sign changes as you go across that angular node as well. And then again, so we change the sign 3 times from plus to plus and back to minus as we go across first the radial node, then the angular node, and then the radial node again. Here's another kind of larger scale picture of the 3pz orbital for chlorine. And what you're seeing here is the different probability of finding the electron at this distance of 0.1. So it's more likely to be here than it is to be here at 0.0316, right? And we can define the size of this orbital by how certain we want to be that the electron is within that. If we define it at 90%, then just what's inside this 0.1 shows up. If we want to be 97%, right, then we need to have everything within the volume of the 0.0316. Right? So that changes not the overall shape, but the size of the lobes. And then we have this radial node again, right? And here's the 3D x squared minus y squared orbital showing the x equals y and the x equals minus y here and the x equals y lobes. And then the 3dz squared orbital. The 3dz squared orbital has some strange looking kind of parabolic nodes within the torus, which are a little bit odd. So nodal cones instead of nodal planes. These don't have any radial nodes. They have 2 total nodes because the total number of nodes is equal to n minus 1 and is equal to 3 here, so it's 2. But 2 nodal planes for the 3d x squared minus y squared and 2 nodal cones for the 3d z squared. So this shows kind of an overlay of the wave function itself, psi, for n equals 1, L equals 0, that's the 1s orbital. For n equals 2, L equals 0, you'll notice that the sign on the wave function changes as you go across the node. And for the n equals 2, L equals 1, where the node now is the xy plane or the xz plane, right? So there's no radial node. And then for n equals 3, L equals 0, 2 radial nodes. For n equals 3, L equals 1, there's the 1 angular node and then 1 radial node. And then for n equals 3, L equals 2, there's 2 angular nodes, and so no radial node. And then here we have the r squared psi squared, that's the radial probability function. So the wave function is very high at the origin, but the radial probability function is 0 at the origin because there's no volume there. Right? The radial probability function is what we're plotting in 3 dimensions when we show you those surfaces. Right? So for n equals 2 and n equals 3, the most probable distance gradually increases. Right? For L equals 1 versus L equals 1, as you go from n equals 2 to n equals 3, the most probable distance gradually increases. But then, because of the inner lobe, right, there's that node there, because of the inner lobe, the p orbital is held more tightly than the d orbital, and the s orbital is held more tightly than the p orbital, right? You can see that for the azimuthal quantum number, as the azimuthal quantum number goes up, the most probable distance becomes closer to the nucleus, but the inner lobe is the reason why the p orbitals are held more tightly than the d orbitals, so the d are higher in energy, and the s orbitals are held more tightly than the p orbital, so the p orbital is higher in energy. And this is just the same thing. Here are the f orbitals. They're really not worth worrying about, but for the 4 f orbitals, you'll notice now there are 3 angular nodes, so there are 3 nodal planes. For if the f, x, y, z, there's a nodal plane at x equals 0, a nodal plane at y equals 0, and a nodal plane at z equals 0. So anything that makes the product x, y, z equal to 0 will be an angular node. So the xy plane, the yz plane, and the xz plane are all nodes. These lobes lie in each of the 8 quadrants. For the f, y, x squared minus z squared, anything, so y equals 0 is still a node, right? Y equals 0, which is the xz plane, that's still a node. There's nothing that lies on the xz plane. But now x squared minus z squared can be 0 at either x equals z or x equals minus z. Right? So your other 2 nodes are not on the Cartesian planes, they're off the Cartesian planes, like the d x squared minus y squared orbital. And so you've got an x squared minus z squared, an z squared minus y squared, and an x squared minus y squared. So those have the same shape. Some of the lobes lie in the plane, and some of the lobes lie out of the plane. And then you've got these weird ones with the double torus that have nodal cones, right? 2 nodal cones and 1 nodal plane. So for this one, the xy plane is still a node, right? But then you've got a nodal cone here and a nodal cone there. You don't really need to know what the f orbitals look like. Here's the fxyz actually showing the planes, right? The xy plane, the xz plane, and the yz plane are all nodal planes, and you've got your 8 lobes, right, in there. So for the 4f orbital, the number of total nodes is equal to n minus 1. The number of angular nodes is equal to L. L equals 3 for an f orbital, which means there's no radial nodes for the 4 f orbitals. Well, hopefully that helps a little bit, because we're going to be working a lot with these atomic orbitals, mainly just the s and the p orbitals, as we form molecular orbitals from them.